Okay, so last week we actually completed our design pattern for observer, and also we talked about before the observer how the one-directional design wouldn't actually work. And let me just tell you the plan for the final week. It's the last week today. For that particular lecture, if you go towards the end of the lectures page, let me show you quickly. Okay. If you see over there, I got all the resources for you for the observer pattern. There's one single bit for that particular lecture called event-driven design. I didn't have time to finish that last Friday. I will see either I will give one more extra lecture maybe this Friday, or maybe I'll try to refer you to some previous video. I'll try to see which one might work better for you for your learning. But for today, we have to start a new lecture. We need 2 classes to actually cover this topic at least. Okay. So now we talk about a different topic right now. So it's not really design pattern, but I would say that's a very fundamental topic and also a very fundamental learning outcome for this course. And remember, on day 1 of this course, I emphasized the importance for writing contracts, like a specification. For every command or query you write, you always equip them with precondition and postcondition. So you would know when you actually test your function at the runtime, you will know whether it's actually the client to be blamed or the supplier to be blamed when either precondition or postcondition fail. But now, this particular lecture, we want to really draw connection to your previous course in 1090 about predicate logic or propositional logic, about discrete math. And now, whatever you learn from this particular lecture here will be very valuable. Later on, when you go back to your development in Java, Python, C#, anything, right? So whenever you got any control structure or data flow in your particular programming language, you can always apply this particular approach to verify on the piece of paper the correctness of your program. Okay, anyway, I'll try to make some remark if I have time at the end. But anyway, so this lecture here is going to be more about math, but it's also kind of an interesting lecture. Okay, we need 2 classes today and also Wednesday to cover that. And the first few slides, we just want to warm up a little bit, just to clarify some terminology. Maybe you have been exposed to this terminology back in 1090, but maybe it's been a while. But let's do a very quick review, only about 2 or 3 slides. First of all, we talk about assertions. You can think about assertions are more like checking if a particular Boolean condition is true at some point of your program execution. For example, precondition is an assertion that's checked before you try to execute the body of your implementation, and postcondition is just another assertion that's actually checked at the end of your programming implementation, right? They're both assertions. And we want to distinguish between weak and strong assertions. And notice that weak and strong, they are more like a relative notion. Every time you talk about an assertion being weak or being strong, you don't really mean they are very weak or very strong. You want to say one assertion is weaker than or stronger than the other assertion, for example. And the way for you to think about it is think about every assertion like a Boolean condition. You can want to imagine the meaning of each assertion is a set of satisfying value. For example, let's compare these 2 assertions. The first assertion is x larger than 3. The other one is x larger than 4. And now given these 2 assertions, we want to somehow judge which one is weaker and which one is stronger, or their equivalents. Apparently, you can see these 2 assertions are not really equivalent, right? So one must be stronger than the other, and vice versa. So now the way to think about it is a very fundamental technique in order to understand the more advanced topic we're going to talk about later. So now think about, first of all, when we talk about x larger than 3, you want to think about the meaning for this particular assertion here being a set of satisfying value. In this case, what do we have over here? You can see we got it's strictly larger than, so the smallest value we have will be 4, and then 5, and then 6, and then 7, all the way to maybe infinity plus, right? Imaginary set. And what about the other one? The other one here, first of all, you want to think about whether the corresponding satisfying value set would be smaller than the green one we just drew, or would be larger than, or would be equivalence, right? That's kind of the question you want to think about. So now let's see for this one here. So now if you think about it, let's first of all draw this set here. So now larger than 4, strictly larger than 4. The smallest value would be 5 over here, and followed by 6, and followed by 7 all the way to infinity. Okay, it's a very simple example, but just to demonstrate the idea about weaker versus stronger. So now in this case, apparently you can see the green one over here. Sorry, let me say it in this way. The red one, the red set over here that we just draw, is actually a subset or proper subset in this case, because we got exactly one value less in the red set. It's actually like this. Okay, let me just draw the okay, it's a proper subset, and then the green one is actually over here, right? So now, to be more precise, think about this is a green set we just draw, and this is the red one. And exactly one value that belongs to the green but not to the red is the value 4. Okay? So now, whenever you got this kind of notation over here, so that means we can say, logically, you know that also x larger than 4 and also versus x larger than 3, right? So now we know that in logic, we can say implication. If this is actually true, it's guaranteed this must be true, but not vice versa. Okay? It's a very quick review of implication. So we have to manipulate implication quite a bit for this particular lecture. Okay, let me say a little bit more. And usually you can think about the, let me just say one more thing. Of course, in general, you can also say it's a subset, right? It doesn't have to be proper subset. Whenever you have implication over here that really correspond to the subset relationship for their corresponding satisfying value sets, and whatever that's on the left-hand side, which has less satisfying value, they are called to be stronger. Okay, let me put it here. Okay, so this is strictly smaller satisfying value set, and we set such assertion over here to be stronger. They're stronger because they allow less value to be included in the set. Okay, and similarly over here, for this particular one over here, this one here, it has larger satisfying value set. Okay, I'm just don't repeat the words, and they're said to be weaker. So now the most important two words to understand will be when we talk about weaker versus stronger, right? So weaker or stronger, either you can think of subset relationship, or you can think about in terms of implication. Okay, guys, any questions so far? It's more like a review. Okay. Okay, if no question here, that's good. So again, before Wednesday or towards the end of today, try to really get used to everything I said as internal logic. That's all you need. Okay. I'll go back there to the slides and I will go on. Okay, we'll talk about stronger versus weaker, and then, okay, exactly what I said, so I don't need to repeat the slides. Oh, sorry, you already saw the answer. Okay, so what is the weakest assertion, right? So now, usually you're given two assertions or a few assertions. You want to find out the weakest, so it's more like a relative. However, the weaker the assertion is, the more value it can allow in its satisfying value set. Apparently, true is really the weakest assertion. Okay, hopefully you can see that. And later on, we're going to see, let me just see one more. What about the strongest assertion? The stronger an assertion is, the less value it can allow in its satisfying value set. So in this case, it should be false, right? Because false wouldn't allow anything to be included in the set, right? It's just empty set, basically. Okay, and we said the set of satisfying value for true would be the universal set, as you learned from 1090. So now, having true and false, they are more like extreme cases. So usually when you write your precondition and postcondition, you don't really want to go into true or false. You don't really want to typically. Okay, so you really want to have something that's so-called contingent, which means it can be sometimes true and sometimes false. Right? Okay, so now let's bring a little bit closer to our context, design by contracts. So now we say a weaker invariant has more acceptable object states. For example, if you say the balance, okay, so let me just give you one more example, right? So now if you look at, let's say, talk about two designs over here. So when we talk about class invariants, first of all, let's say we have this. Let's say design number 1, bank number 1. Okay, and design number 2, we got bank number 2. bank number 2. Okay, and then let's say for bank number 1, we have a class invariance. And also let's say over there we simply got balance over here of type integer. And also here we also got balance of type integer. And then also here we got invariance. Okay, let's talk about 2 design alternative for us. So now let's say for the bank number 1, we got balance, let's say larger than 0, strictly larger than. And then we have over here balance larger than or equal to 0. Okay, again, I try to make it very simple so I can illustrate the idea. So now you want to know, let's say this is I1, okay, and this is I2. So what we really want to know is which one is stronger and which one is weaker, right? So now, a very simple question for you. Which class invariance is stronger? It would be stronger because it allows fewer object states to be valid. So which one? I1 or I2? Which one is stronger? Anybody? Which one? I1. Very good. Thank you, Ken. So I1 is actually stronger because if you think about it, you can think about if this is I1, right? It's stronger in the sense that here I1 can allow balance of 1, 2, 3, all the way to plus infinity conceptually. But now if you talk about I2 over here, you can also include the possibility of equal to 0. So that means when you draw I2, conceptually a little bit like that, the green one. And then the one that can also allow would be 0. So this is I2. So you will have something like I1 implies I2. Okay, so I1 is actually stronger. In the sense that, so now if you have some bank 1 objects at the runtime, right? Say at the runtime. Okay, at the runtime, if you have some bank 1 objects over here, and then it has a balance over here. If I simply got 0 over here, what you will get is going to violate the class invariance. So this will be class invariance violation. Okay, that's for, oh, I should have made it blue, right? So it's actually easier for you to see the color. Okay, color and blue. Okay, so that's for runtime, for bank 1. On the other hand, the class invariance over here for I2 is actually weaker in the sense that it can allow more object state to be valid at the runtime. In that case, if I just draw one more time, okay? So now here you got bank 2, and then you have the balance. Let's say if I still got 0. In this case, 0 is going to satisfy this particular invariance. So now in this case, this will be a valid object states. You can see nothing much that's new. We're just trying to go a little bit further to say every contract you write is simply like a predicate, like a Boolean condition. So we want to study a little bit more about the theory of contracts. Okay. Okay, so now let's go back here. And also, okay, that's just another example here. And also weaker precondition means you can have more acceptable input values. And also for weaker postcondition, you have more acceptable output values, things like that. Okay. Guys, any questions so far? Okay. It's quite a bit of review, but I think it's actually quite important for you to actually understand. Okay. Okay. I presume everybody is good. So now I'm just going to tell you that the next 2 slides are basically just reviewing about weaker versus stronger. So I will leave that for you to read. They are nothing new. Okay. Basically, we just talk about precondition and also we talk about postcondition. And if you compare, okay, let me just give you one. How about we go over example very quickly? You can read the slides, okay? But I'm just going to switch to example very quickly for you. Okay, the first example, okay? Let's say we got 2 versions of the withdraw, okay? We got withdraw version 1, and also we got withdraw version 2. And both of them have some precondition over here. You can see the first one over there is amount larger than 0, strictly larger than. And the second one is amount larger than or equal to 0. Okay, so now which one has a weaker precondition? Withdraw V1 or withdraw V2? Withdraw V2. Thank you. Yes, thank you, Ken. So now what I want to just tell you very quickly, okay? You can see larger than or equal to. Apparently, you can see P1, which is larger than, implies P2, okay? First of all. And now we are talking about these two predicates in the context of precondition. So that means withdraw number 2, withdraw version 2 is more tolerance on accepting input values. So what do I mean? For example, exactly this case. Let's say we have, let's say, two objects. Okay. Let's say we got accounts. If I say ACC dot withdraw V1. In this case, I will say 0 over here. That's one particular command call. Let's say I got another one. Let's say ACC dot withdraw. And then I got V2 over here. V2 and then also 0. Apparently, you can see we are taking the same input value for both commands. But because one's precondition is more tolerant than the other, so now in this case, this will illustrate exactly how this can happen, right? So now you can see over here, for this particular one, so 0 larger than 0 will be false. So this will give you a precondition violation. Because over here, P1 is actually require more. And also we say P2 require less, or is more tolerant. Okay. On the other hand, you can see over here, this guy here, ACC, so this one will be no precondition violation. Okay, hopefully so clear so far. Okay, so now quickly just about postcondition. So now let's take a look over here. And let me just tell you the essence for this particular example. Again, it's just one example. Let's say here we have, let's say F1, and then it has some postcondition here, and then it's simply just Q1. And also we got F2, just another function. And then you will have Q2, right? And also it's postcondition. And the difference really is, in the case of Q1, we have disjunction. And in the case of Q2, we got conjunction, right? So now, which postcondition ensures more? Or put it another way, which postcondition is stronger? Q2. Very good. Thank you. Very good. So now, again, you can see conjunction over here, right? That means both ends must be satisfied. On the other hand, this one only requires that only one of them will be satisfied. Okay. So what you can do is draw a very quick picture over here. Okay. So now if you think about it, let's say for Q2 over here, let's say Q2, it must be positive and also be an even number. So that will be 2, 4, 6, and 8, and etc. Right? And now for this particular Q1, it will be a much larger set over here because you only have to satisfy either one of them. For example, to satisfy this, it can be maybe just an odd number. It can be 3, can be 5, can be 7, and etc. And just to satisfy this, it can be maybe negative even number. It can be -2, -4, -6, etc. Right? You can see the green one is much weaker. So now, when we talk about postcondition, okay, it's really also important to see for the postcondition. So this is stronger, first of all, and this particular postcondition over here is actually weaker, right? Again, it's relative to say which one is stronger, which one's weaker. In the case of stronger, so in that case, you can think about it's a more demanding task for the supplier, because it takes a little bit more effort so that the satisfying set of value is actually smaller, right? So smaller satisfying value set means it's actually more demanding for the supplier to satisfy. Okay, So that's about, again, we talk about assertion. Either it's a precondition, postcondition, or class invariance. Guys, any questions? So far, it's only warm-up before I talk about a new example. Any questions? Okay. So I would say to really gain the most out of this particular lecture before Wednesday, I would suggest maybe review a little bit what you learned back in 1090, the kind of logical proof. But we'll go over some proof today, together as well today. Okay. Okay, seems like everybody is okay. So now let's start with our first example. What we talked about previously were just warm up, right? Just to clarify the terminology. But now we're going to talk about the first example. Okay. Now let's talk about this particular command or feature. Let's say we have a class called foo, and then we have only one attribute called I, okay, of type integer. And then we have a command called increment by 9, okay? And then, well, it's quite obvious what it will do, right? It will increment the value of I by 9. This is the precondition, and this is implementation, and this is a postcondition, okay? So now, here's my question, okay? Let me switch to iPad over here, okay? Again, every time when you talk about, we'll define what correctness really means. But let me just talk about here quickly. When you talk about correctness of any program, for example, the one we just talked about right now is a program, right? When we talk about correctness, it's really relative notation, relative in the following sense. Think about there are two parts of your program. One is about implementation. For example, you can see this part over here is your implementation. And also you have specification. And specification, let's say as far as the routine or feature is concerned, so you have the precondition over here, and also you have the postcondition over here. So these two together is called a spec. Okay, and whenever you talk about correctness over here, you really talk about implementation satisfies the specification. Okay, a very quick emphasis. Always is relative when you talk about a program being correct. And of course, later on, we're going to talk about how you can formally prove or disapprove the correctness of this particular program. But for now, can anybody tell me intuitively, do you think this program is correct? Intuitively. If you do believe it is correct, give me some reason. If you don't think it is correct, give me some reason as well, right? So for example, if you don't believe the program is correct, maybe this is what you can do. Having some valid input for increment by 9. Any input that satisfies the precondition, and you try to execute the you try to execute the body of the implementation, and then is it always guaranteed that you will actually have some value that will satisfy the postcondition? Is always the case. If there's under any circumstance you're not going to get it, so that means your program is not correct. I already see some correct answer from Ken. Okay, so now I'll pause a little bit for everybody to think. Let me rephrase my question again, and then let me so that when you later review this material, it'll be easier. Okay, this part is this part here, pre and post condition, they are called specification, and also this part here, the blue part, is called implementation. What we want to really make sure is, given valid input, which means the precondition is satisfied. Which means the precondition is satisfied. Executing the implementation. Well, two things over here. Number one, it will terminate. Okay, for termination over here, I would say let's now be a little bit informal in terms of our justification. Because there's no loop over here, so there's no possibility that you can run into infinite loop, and also there's no recursion. So terminate, we'll talk about it a little bit later. Okay, and number two, upon termination, the postcondition is satisfied. Okay, so this is really what I mean by correctness. I think that's more or less how we will formulate the correctness notation a little bit later. Okay, so now the keyword over here, you talk about valid input over here, and also you talk about executed implementation, and eventually you want to say it will terminate, and also you will satisfy the postcondition, right? So these are the keywords you want to pay attention to. And many of you, actually, why I'm trying to explain, many of you also told me the right answer. So now let's try to say the correct answer is this program here is not correct. Okay, and when you want to prove something that's not correct, you can simply give one counterexample. You want to give one counterexample to this notion about the correctness over here. So now many of you gave me the correct answer. Let's say some valid input. What about I'll give you number 4. Okay, let me just give you here. Let's say 4. So this would be our counterexample. Let's say we got input value 4, and then when you execute the implementation over here, you would say I is assigned to I plus 9. So now I would just be 4. 4 plus 9 will change I to be 13. And now ensure over here 13 larger than 13 is going to be false. So you have some postcondition violation. Okay, so now upon termination, the postcondition here is not satisfied because you got I, which in this case, I would be just 4, right? That's the value we choose. So you can say 4 plus 9 larger than 13. So this one here is just evaluate to false. Okay, guys, that's how we can informally justify why this program is incorrect. Okay, we'll deal with this more formally. As you can see, when you are doing things informally, there are quite many things you have to write down in order to prove it. But later on, we'll see a much neater form of proving it formally. Okay, any questions? Okay, good. So now let me do a similar example over here, very similar. Okay, guys, how about this? I just modified that a little bit. Again, take a look at this, and then I got precondition, postcondition, and then we have implementation. So now, is this program correct? Okay, I heard yes. I also heard no. I'll be more interested in, okay, first of all, how about this? It seems a little bit like a dilemma over here. I can tell you why. You might think it is correct in the following sense. For those of you who might argue it is correct, you might think in following. What would be the valid input for I? It would be 6, it would be 7, it would be 8, and etc. So these are all the valid input values. Okay, let me just change the color a little bit. Okay, so these are the valid inputs, which means, for example, if you try here, 6 plus 9 would be 15, larger than 13 would be true. 7 plus 9 would be 16, larger than 13 will also be true. So every valid input you chose over here, given that it satisfies this precondition here, is guaranteed I larger than 13 will be satisfied. Okay? So now in this case, if I is any one of this, I larger than 9, I plus 9 is guaranteed, is always larger than 13. So this is how we can informally say it is correct. Okay? This is how you may argue that it is correct. Okay? Hopefully so far so good. Again, the notion about correctness I said before, please make sure you review it and make sure you're convinced. On the other hand, for those of you who may also argue the following, you might think it may not be correct. Okay, I will put a question mark over here. It's a little bit it may be a little bit convincing to you. Okay, I'll try to explain to you. For those of you who might be thinking it's incorrect in the following sense. Here, I larger than 5, which is the precondition, right? You might argue it is stronger than necessary. When I say it's stronger than necessary, so let me try to, you can see I'm starting using the term that we introduced in the beginning of the lecture. When I say stronger than necessary, what I really mean by this is this. It will disallow some input value that actually would not cause any postcondition violation. So can you tell me which value it is? Well, so now in this case, okay, I'm not sure if you, okay. Actually, the argument I'm trying to make now is also valid, okay? It's stronger than necessary. So how can I give you the example, right? Stronger than necessary. For example, okay, good. Thank you. So now one of you actually said that correctly, exactly. So that should be 5, exactly. Let me write it down. So now let's say value 5. If you think about 5 over here, currently 5 larger than 5 is actually going to give you false. So currently 5 is currently not considered. Currently not considered a valid input. However, let's say tentatively, if we actually allowed the value of 5 to be taken as input, are we actually going to get any postcondition violation? The answer is no. Okay, let's say if 5 was allowed, hypothetically, in that case, 5 plus 9 is actually 13. Oh, sorry, 14. Beg your pardon. 5 plus 9 would be 14. And 14 larger than 13 will still be actually true. So that's actually okay. So which means 5 could have been included in the precondition valid input value, but it was not. Should this be a problem though? Okay, so I would say for the hopefully you can follow my thread of thought over here. Okay, so now I would say this particular one here. Okay, I would say, okay, whether a precondition is too strong or not, it's up to the designer of the command. For example, maybe for some particular reason, maybe for you, you decided that 5, even though 5 would be okay to actually establish the postcondition, but for whatever reason, you just did not want to allow 5 when the client tried to pass the value 5 for whatever reason. It's actually okay. So what's really important over here is you want to make sure is, so here's a critical point. I mean, we're trying to make that, okay? The guiding principle for your precondition over here is cannot be too weak. So this is the most important point. Cannot be too weak, which means it cannot allow some value for input that will actually cause some postcondition violation. For example, over here, you can think about this particular precondition here is too weak. For example, it would allow 4 to be the valid input. Okay. Okay, guys. Any question about these two examples? Right. I think these two examples again they are quite simple, but it will illustrate some points. Let me answer some question. Okay. Can we also argue that the postcondition is too weak? Yes, indeed. Let me bring to another general point. Indeed. So now I would say just in the following way. Think about how the program verification or program correctness is going to proceed. Okay, let me just give you a general picture. Okay, think about whenever you are done with one version, let's say version 1 of your implementation and also specification, you simply got feature F, and then you got require, let's say require P, precondition, and also you have do. I would say S for statements is like a postcondition. Okay. And also, let me just be a little bit more consistent with the labels we're going to use later. let me say precondition is Q. And also ensure this R. Okay, let's say this is my particular design for my program. Contracts, and also I got implementation, right? So now somehow I just want to somehow have a way to verify whether S can satisfy the implementation can, okay, verify whether when Q, the precondition, is satisfied, executing the programming statement S will establish R. Okay, we'll see exactly what would be a systematic way of doing this, but let's say this. Okay, so these are the three components for your program. And now let's say if you encounter situation like this or situation like that, what should you fix, right? I would say in general, you don't necessarily have to make your precondition that was way too weak stronger. You can sometimes try to go the other direction to make your postcondition maybe a little bit stronger or weaker. So I would say the fix. When you justify that your program is incorrect, what should you fix? You may fix, I would say again, is you can either fix Q, you can either fix S, you can either fix R, right? It's like a redundant, right? Basically, my point is when you as soon as you prove that your program, the current version is actually not correct, you don't necessarily always have to only touch the precondition. You can actually maybe fix the precondition to make it stronger or weaker. Or you can maybe try to fix your postcondition to make it stronger or weaker. Or you may have to fix maybe some coding of your implementation. All is possible, okay? But in the example we see, we'll be more specific of what you have to fix. Okay, guys, any questions? Okay, very good. You're welcome. Okay, so now let's take a look at the slides. Okay, exactly what I just said. You can also look at the slides. We have discussed these already. Okay, software correctness. Okay, I already talked about correctness being a relative notation, and you want to make sure it's consistent with the specification. And then that means we need a specification. Okay, contracts, precondition, postcondition, and class invariants. And for those of you who are taking or have taken 3101, the algorithm course, I'm sure you learned about the notion about contracts for loops, which will be loop invariants and loop variants. We'll see that on Wednesday. Okay, for today, we'll just do the basics. Okay, so now you want to learn, in order to really do some systematic calculation for proving the correctness of your program, you have to learn a little bit about the notation. Okay, the notation you have to know for the rest of this lecture here is this notation here. You see curly brackets and also curly brackets. Let me show you exactly how to do that. Okay, so what I would do is, let me just copy this particular program over here. Okay, okay, one program here, and then let me just do the other version very quickly. Okay, so these two. Okay, so this is the one we said as incorrect, right? That's what we justified. That was incorrect. Okay, let me just put it in red so that you know that's incorrect. And the green one, it may be correct because we really want to disallow the value of 5. Okay, so now, so this, if you think about it, so this is the notation. The notation is something called Hoare triple. Let me write it down. Okay, let me just move this a little bit down. Okay, it's called Hoare triple. So this particular verification method was developed by a researcher by the name of Hoare. And many of you may not have heard about this person here, but you have actually made use of his work a lot in the previous course. Okay, so have you heard about the method called quicksort? I'm sure you have, either from 2030 or from 2011. The quicksort was developed by Tony Hoare, and the Hoare triple, which we're going to talk about in this lecture, is also developed by Tony Hoare. He's a very well-known researcher for software engineering. Okay, anyway, it's just a historical background for you. Okay, so now let's take a look. Syntax for the Hoare triple goes like this. You have to, first of all, you have to put curly brackets over here, 2 pairs of curly brackets here. You put something here, you put something here, and you put something here. Okay? Whatever you put over here will be the precondition for your particular method or feature. Precondition. And whatever you put over here will be the postcondition. So now you can see that these two guys, the orange one over here, they should be Boolean conditions, right? And then in the middle, it should be some program. Okay, it can be as easy as some simple assignments like this, or it can be as complicated as some loop. Okay, we'll see that. And now, how do we write it? Very easy. So now if you want to translate it, you can see this part is the pre and post condition. So you put precondition I larger than 3. And this part here will be I larger than 13. Okay, if I do something very similar for the other one, let me do that quickly, right? So now let's say for this particular program. So here, this Hoare triple is just for this particular program, right? Just this one here. Let's put another one here. So now I have precondition here, implementation, and postcondition. So now in this case, it's going to be I larger than 5. Postcondition, I larger than 13. Right? Pre and post condition. What should be put in the middle? The implementation. So now in the implementation, you can see the first one is I is assigned to I plus 9. And also this one here, I is assigned to I plus 9. Right? The implementation. Okay, guys, any question about the syntax for the Hoare triple? Right? I'm just trying to show you basically the idea would be given any arbitrary program over here, you're going to turn that into the Hoare triple so that you can start proving. Similarly, given this particular program over here, you can also convert that into this particular Hoare triple and then start proving. Okay, and apparently in this case, as we argued informally before, we know that since this particular program is actually incorrect, right? We said that before. It is incorrect, so that means this Hoare triple over here, the whole thing. Think about a Hoare triple is like a Boolean predicates. Whenever you state a Hoare triple for a particular program, the Hoare triple can either be proved as a theorem, which it can be proved as true always, or you can find some counterexample. So now for this particular Hoare triple, it cannot be proved as true, or cannot be proved as a theorem. Okay. On the other hand, for this one here, the second Hoare triple over here, for this one here, given that this source program over here is actually correct, so we know that this particular Hoare triple, it can be proved as a theorem. And of course, typically, if you want to prove that the corresponding Hoare triple is not a theorem, you will typically give some counterexample. Okay, now let me write it more properly. Counterexample. Okay, guys, any question about the syntax for the Hoare triple? But exactly how you prove that a Hoare triple is actually a theorem or not, we're gonna see that. Okay, summarize very quickly. So now, given some program, okay, a little bit repetition, okay, if you got require precondition here, and then do some implementation S over here, and also postcondition, and then let's say R over here. So this is your input program. Oops. Okay. Let me just draw that more properly. Let's say this is my input program here. Okay. You can think about this as input. What we will do for the rest of the lecture is we try to formulate. We try to formulate this into a Hoare triple, which looks like the one we just mentioned, right? So now here, it will be, first of all, precondition, and then implementation, and then postcondition. And think about this Hoare triple here is basically a predicates, which may be proved or disproved. Okay, exactly how you do that systematic proof, we're going to see. Okay, guys, any questions? We okay? Good. Okay, let's go back to the slides and then do a little bit more. So now that's the Hoare triple here. And then exactly what I said. So now in this case, this program is, okay, you can see these are the two different programs. And now if one can be proved true, then the original implementation is actually correct. Okay, so what I meant by was, so now if in the case where it can be proved, so that means that means S is correct with respect to, okay, with respect to is very important. Again, correctness is a relative notation. S will be correct with respect to precondition Q and postcondition R. Okay, that's basically what the slide is trying to say. Okay, so these are just two examples I just talked about, right? You can look at that. Okay. Okay, Hoare logic, just a little bit more background. Okay, let's see. So now implementation S, and then we got precondition Q and postcondition R, right? So now let's, it's called the correctness predicate. You can either say, what you can say is over here. So I would say both names are fine. Either you can say it's a Hoare triple, or you can say it's a correctness predicates. Okay, correctness, because it does consider all the three parts of your program. Okay, so then, so what does, when you have a Hoare triple, when will Hoare triple be proof is true? Okay, in that case, let me just tell you the meaning. Okay. First of all, the program should terminate. You will see exactly the definition I'm giving here is how I lay out the correctness definition in the previous page, right? Remember very quickly, and I can just show you the slides. Remember this particular informal notion that I talk about correctness? Okay, this is exactly how I'm gonna use the Hoare triple to prove. So now, when I have a Hoare triple over there, okay, I'll get to there. So now it's saying that as the program must terminate, and then you want to say that S start executing in a state that satisfies the precondition Q, and then afterwards S will terminate, and also it will satisfy R. Okay, so A and B. So A and B are two separate concerns when you do the verification, especially in the case where you got loops in your implementation. You want to prove, number one, termination, which is A. Number two, which is B, about if it terminates, it should establish the postcondition. So these are two notions of correctness. And we say that in the case where you only talk about B, you can see B here does not involve any notion about, well, item B here does not require any proof explicitly about the termination, which is assuming that S terminates, it will generate it will satisfy the postcondition. So that's why B is called partial correctness. And without proving A, B is only partial, basically. But if you can prove both A and B, in that case, you call it total correctness, right? So now you have a notion between partial correctness, where termination is simply assumed, and versus total correctness, where both the termination and also partial correctness is proved. Okay, so these are the two concepts you have to also learn. Okay, any questions about partial correctness versus total correctness? Okay, good. So now let's go a little bit more deeper into Hoare triple, okay, before we talk about its systematic calculation. Let's say we talk about what you can think about the Hoare triple is also like a contract view for the your program. Because if you hide S over here, you can see there's a precondition and there's a postcondition. So these are the contracts for implementation. Let's try to understand a little bit more by considering different possibilities for the pre and post condition. Okay. So now let's talk about different possibility. Let's say this. If I have a Hoare triple like this, so what does that really mean? Okay, I'll pause a little bit. You can feel free to answer me, but if you wish. But for every one of them, I'll pause a little bit for you to think. Basically, for the rest of this particular slides, I'm just going to give you different combinations of precondition and postcondition, right? And one of you said right there, very good, all the input values are allowed. So now you can see this. This is the weakest possible precondition for your implementation, right? You say any input value should be allowed. So this is, yeah, all the input are valid. So this is most user-friendly. However, be careful, this might mean it's kind of symmetric. If it is so friendly for every user because any value passed by the user will be okay. On the other hand, that means your program must be good enough to handle all the possible inputs. How about this? If I got the precondition being false, so now that means the clients would be very frustrated, right? Because any value they pass will be considered as not satisfying because there's no set of values that will satisfy false. So this will be, so all the values are invalid. So that's kind of useless to the clients, right? If you design a program such that it's simply just false as a precondition, might be very easy for you as a supplier, but your customer will be very upset because nothing they can actually pass to your program to run. How about this? So now we are moving to the post-condition end. So let me put it this way. If I have this particular program, do you think it is very easy for the clients or very easy for the supplier when the post-condition is actually true? Guys, any thoughts? Yeah, it should be easy for the supplier. Very good. It should be very easy for the supplier because any output values would be included in the universal set for the true. For example, if you want me to sort one array, that would be what you as a customer is expecting me to do. What I can do is I can simply print out hello world back to you. And printing out hello world will be one of the satisfying value for true. Okay, so now having true as the post condition is not very good for the clients, right? So for you as a client, you must make sure the supplier specifies the contracts, the post condition, as complete and as strong as possible. Yes. Okay, all the output value will be valid and it's very risky for the clients. And one of you is making a remark because they don't have to do anything. Exactly. Supplier doesn't have to do anything. It can just be empty implementation. But even worse, the supplier might do something malicious. They might do something very bad for the object states, but they can still satisfy true. So that's not very good. You can see going for extreme in either end is not good. Finally, how about this? If we have a Hoare triple like this, it's actually harder for which side? Should be for the supplier, right? Because now that means even if you can come up with the quickest sorting routine, it will still be false. You will never be able to satisfy. You as a supplier, you can never generate any output value that will satisfy the false because false corresponds to empty set, right? So that will be very hard, very challenging coding task, maybe not even feasible. Okay. Finally, what about this? True and true. Okay, true and true over here. So this is some concluding remark I would like to make for this particular slides. If you think about true and true over here, it's almost like when you first came to this course in day one, when you are not so used to the idea about contracts, that you always should really put precondition and postcondition as contracts between the supplier and the clients. But now, if you simply put true and true over here, it's as if they were not there. It's as if there's no binding between the client and the supplier. So that's also not good. So you wouldn't know when something really goes wrong at the runtime. We said a good design means when something goes wrong at the runtime, exactly one party should be blamed. Now in this case, if both are true, no one is to be blamed. So that's not good either. Okay, so guys, so now we come to systematic calculation for systematic proof for Hoare triple. Okay, so now we want to go a little bit further. Okay, now we need to explain something called WP. Okay, WP here. Okay, you can see WP. So we want to prove whether the Hoare triple, which is a predicate, whether it should be a theorem or not, and using some concept called WP. And WP stands for the weakest precondition. Or put it this way, we want the precondition for your program to be as weak as possible, but it cannot be weaker than the weakest precondition. Okay, something like that, right? Very, very informal sketch. But now before I show you exactly how to prove the correctness of your Hoare triple, let me show you WP very quickly. Okay. So now let me show you this diagram here. Again, as I said in the very beginning of the lecture, it would be very beneficial if you think about every assertion that we talk about, precondition or postcondition, using a set. So it will be the set of satisfying values for the assertion. Okay, so let me try to go over this particular calculation with you. Okay, eventually we want to conclude something like this. Okay, eventually, but let's not get there just yet. So what I would say is, let's think about a little bit backwards. Again, let's review this particular this particular thing here. Okay, if you think about it, okay, let me try to say verbally again. We say that this Hoare triple is actually true if the following is the case. Starting with the states that satisfy the precondition Q. When we try to execute S, it will terminate, and also upon termination, it's going to satisfy R. Right? That's how we define when the Hoare triple is going to be a theorem, which means the program S with respect to QR is actually correct. But now, in order to prove it, we have to do a little bit of mechanical calculation. We have to follow certain rules. So now, think it this way. Think backwards. First of all, we start with R over here. So R is basically all the post-state value you want to establish. Okay? All the post-state values resulted from implementation. Okay, all the post-state value that will be defined by this. For example, if you say the postcondition should be such that, for example, x is assigned to old x plus 1, for example, it would be corresponding to a certain set, right? Just any postcondition, right? So now let's say R is simply all the satisfying value for your particular expectation. And now, given R, and also given the implementation S over here, so given these two things. So now, given the pink and given the blue, we can calculate something so-called the weakest precondition. Okay, let me just highlight it. Okay, so now let me just write it down, exactly what that means. Given some implementation S, and also given some postcondition R, we can calculate another Boolean condition. Okay, so this is so-called the weakest precondition. Weakest precondition for S to establish R. So now it is called the weakest in the sense that any input value not satisfying the WP over here, satisfying WP, should be invalid. Okay, we haven't really talked about exactly how you can calculate WP. We'll get there. We'll get to some simple rules towards the end of today. We'll get there. Okay, so now just one important thing to remember: whenever you want to calculate the WP, if you think about WP, it's more like a method, and the method will take two parameters. The first parameter will be some code, and the second parameter will be some Boolean condition for your postcondition. Okay, so now conceptually, given R, given S, the corresponding weakest precondition will just be another set because weakest precondition is just a predicate. So now in this case, I'm just going to the weakest precondition here. Okay, think about this is the weakest precondition. So now conceptually, the weakest precondition simply means any value that's within the weakest precondition is guaranteed starting from this particular state. If you try to execute the body of the implementation, you will guarantee to end up in a state that's in the postcondition. It's guaranteed. On the other hand, if, for example, think about some value that's outside the weakest precondition. I'll just give you one very concrete example. For example, let's say if the WP, let's say, is x larger than 0, for example, right? So if the weakest precondition is x larger than 0, that means x being 1 or 2, for example, it can be 1, it can be 2, it can be 3, it can be 4. So for example, when x is equal to 2, it's guaranteed executing the implementation will give you some valid postcondition states. On the other hand, if you try to go with any value that's actually not allowed, which means it will satisfy some weaker predicates. If you go to any, if you got any value that does not satisfy the weakest precondition, for example, x equals 0, you can see this one's outside the WP, or simply does not satisfy the WP. In that case, it will be the case that if you try to start with this particular states, for example, and unfortunately, if somehow your particular postcondition, oh sorry, let me say it again. The weakest precondition over here, given R and given S, you can calculate the theoretical weakest precondition, and the weakest precondition can guarantee any value that's within the weakest precondition can really end up being in a state that's in the postcondition, right? That's about the weakest precondition. We'll see how you can calculate it a little bit later. So what does it really mean when your particular program is not correct? For your program to be not correct, that simply means if somehow your precondition is something like this, it's like a weaker set. Let's say if somehow this is your Q for your particular program. If your particular program actually includes the value that's outside the WP over here, in that case, you will consider your program is actually not correct because it allows some value that will not end up being in R. Okay, let me just go a little bit, just once more. Okay. Hey guys, it's very important. I try to cover as many details as possible, but let's just see once more. Okay. What you really want to see is like this. Okay. Let's just see one example. Okay. Let's see the example here. Okay. So I don't need to redraw. Remember this particular program over here. So now remember this particular program is correct. Oh, sorry. This particular program is not correct. This particular program is not correct. Okay. So now the WP over here. Okay. So now I'm not going to talk about exactly how you can calculate it, but for now, just assume we'll see exactly. So now for WP, for implementation, I is assigned to I plus 9 to establish I larger than 13. Okay, so this is how you calculate WP, how you write it. And now this WP over here, so now for now, take it for granted. It's not going to be I larger than 4. Okay, can we just take it for granted? So now for WP, it's simply I larger than 4. Take it for granted, just for now. And then for our particular postcondition I over here, it will be I larger than 13. And then we also got our implementation over here, which is I is assigned to I plus 9. Given this, given that, we can calculate the WP over here, and then we get something like this, which we'll take for granted for now. Okay? So now, what does it really mean when your program is not correct? Your program will not be correct if somehow your program's precondition is even weaker than the weakest precondition. Okay? Over here, let's say this. That means incorrect program. Because the Q, which is the precondition here for your program, right? Because Q is weaker than the weakest precondition. So now, more precisely, when you say it's actually weaker than the WP, it allows certain value that is not going to end up in the valid state for the postcondition. So now in this case, for example, you can see the Q over here, it allows I is equal to 4, right? Like what we talked about before. So now when I is equal to 4, is actually allowed by your particular program. And this is outside the WP calculation. WP is the theoretical weakest precondition. If you got something that's outside the WP, but that value is also allowed by your program's precondition, so that means your program is not correct. Okay. Guys, any questions? I think what I have been talking about so far, just about WP, its meaning. We haven't talked about how you calculate it. We'll get there. Okay. But to really understand the picture here, to really say, given implementation, okay, and now from the two ends, you got the postcondition you want to satisfy. Somehow we can calculate the theoretical WP over here, and then all you gotta check is to see whether your particular precondition for your program should be no weaker than. So that is why you will see this particular implication here. Let me write it down here. Again, think about the process. It's more like a backward process. Given your implementation, given the postcondition, you can calculate the WP, first of all. Okay? And also, you have your particular program's precondition. You want to make sure Q is no weaker than. So this means Q does not allow any value that does not satisfy the WP over here. Okay, it's a very, very important concept. Okay, let me just give you one more example, and then if you got questions, please type on the chat program, and then I can try to I will try to help you with that. Okay, okay. So that's so in this case, this is the input precondition that's actually weaker than the theoretical weakest precondition. So this is incorrect. Okay. On the other hand, let's take a look at another one. Okay. If we look at this particular one, let's say we got the same postcondition. So this is the postcondition over here. Okay. So this one here is I larger than 13. And then the implementation is also the same as before. I is assigned to I plus 9. And now we're going to take it for granted to say over here the weakest precondition, the weakest precondition is just going to be calculated somehow. We'll look at how we do that. For now, take it for granted that WP over here is simply I larger than 4. Okay, and your program would be considered as correct if your program's your program's precondition. Okay, let me just try to be careful. So now your program's precondition over here, it cannot be weaker than. So that means as long as it's enclosed within the boundary of the weakest precondition, that'll be okay. So what this really means is every valid input of your program. And when I say valid input, as long as they satisfy I larger than 5. And I larger than 5 is actually exactly this predicate over here, right? So every valid input, for example, 6, 7, and 8, every one of them satisfy the weakest precondition, right? Every valid input of your program satisfies the WP. Okay, so now finally I want to make a point, and then I'll take a question. So now, that's why when you go back to the slides over here, if I am given this particular Hoare triple, I got precondition, I got postcondition, I also got implementation, right? And now, it would be, in order to prove that this Hoare triple is actually a theorem, I need to do 2 steps over here, right? I'll write it down. Again, let's say this. Okay, let's say feature F require Q do implementation S and also ensure R. Okay, so this is my program. Okay, so this is my program. And so now, let's say in the exam or in well, let's not talk about just exam. I think for your future developments, right? Later on, if you want to ask yourself, if I got a particular program I wrote, I want to justify formally whether or not it is correct. So these are the steps, okay? Think about this is your program with specification. Step number 1, formulates into Hoare triple. In that case, you have Q and also implementation S and also postcondition R. So this is step number 1. Okay? And step number 2. Given this particular Hoare triple, you want to first calculate the WP. And you just need this, right? The implementation and also the postcondition. Calculates the WP for S upon termination to establish R. Okay, that's step number 2. And then step number 3 over here, you want to make sure the actual precondition is no weaker than the WP, right? Think about if the WP is actually over here, you want to make sure the input, all the value over here, only the value, okay, how about this? Only the values in the WP should be considered as valid inputs. Only values satisfying WP should be valid input. So that means your particular precondition Q over here, the Q, it could be like a subset of WP. So that means your program is correct. Okay, so now you want to prove the following. Prove or disapprove. The following. So WP for S to establish R. So we'll talk a little bit about how you can calculate WP for some simple cases. But for now, maybe for today and next on Wednesday. Let's say once you do the calculation, you want to make sure you can prove such implication. So now it's Q. Q should be no weaker than, or maybe stronger than, right? If you think about a satisfying set, like what we are talking about over here, it would be like a subset, right? You think about the Q is a green one over here, right? The WP is the pink one, okay? And then here you're trying to use a subset relation, okay? It's a subset relation, so you want to prove implication logically. Okay, so any questions? I think so far we have been very careful to set up the background for you to understand. Okay, let me just read some questions from Reindeer. Hoare triple makes sure that the precondition is not weaker than the WP, but how does Hoare triple make sure that it is not too strong? Ah, good question. What Reindeer is actually saying is a very good question. Okay, again, let me try to rephrase your question a little bit. let's say we calculate WP for your particular implementation. Okay, so that's a postcondition, that's the implementation, right? And now to really prove the Hoare triple is actually a theorem, you would say the precondition, so this is the precondition, right? Actually implies. Okay? So you can think about informally over here, this particular implication makes sure Q is no weaker than that. And what Randy's question was, what if does Hoare triple actually worry about whether Q is too strong? Or put it this way. If WP is like over here, WP for S to establish R, all we care is Q must be as like a subset of WP. So what would be the extreme case? Well, what would be the case where there's always a subset for any arbitrary WP set? Is there a set that is the subset of any set? Guys, you see what I mean? So now, put it this way. What is the Q, the precondition that is always, oh, how about this? That is weaker than, what is the precondition Q that is no weaker than any WP? Yeah, exactly, when Q is actually equivalent to false. Exactly right. So that means when your Q, no, we should talk about logic, right? If you only set your Q to be just false, and we talk about when the precondition is actually false, right? So that means you have a function f, and there you simply say require, and then false. If you got a program like this where the precondition is simply false, by definition, this program is always correct, because there's no way for things to go wrong at the runtime, because everything will just be blocked by the precondition already. You never get a chance to go to the implementation to execute it, right? So now, if the precondition is false, by definition, this program is correct, because false implies anything. However, at the same time, you also want to make sure your program is not so useless, right? Having a postcondition being too strong is also not good. Okay, so now let me just summarize what your question was. Okay, Hoare triple proof using WP only makes sure your precondition is not too weak, right? Because we're proving implication. But now, whether your precondition is too strong or not is beyond the scope of the Hoare triple. In that case, you have to do a little bit more further analysis, which is beyond the scope for this particular lecture. Okay, whether Q is too strong is beyond the scope. Okay, hopefully that answers your question. Okay, so now let's go back to, we got about 10 minutes. Very good, very good. Okay, so guys, let's do something very quickly. So we talk about WP over here. And now when you talk about WP, again, WP is more like a method that we're going to define, like a function. And the method takes two arguments, S and also R. S is simply program code. It can be assignments. It can be alternation, like if then else. It can also be sequential composition. Okay. Hopefully today we got about, let's say 10 minutes. I don't want to run too much over time. Just give me 10 minutes. At least we can finish about assignments, okay, to give you some intuition, and then we can carry on from Wednesday. But I would say today, I'm actually quite happy the way we actually went through the space. It's really important for you to make sure everything we said about WP, Hoare triple, weaker versus stronger, and correctness, partial correctness, etc. Make sure you're comfortable with them before you attend Wednesday's lecture. That will help. Okay, the programming statement here can be assignment, alternation, sequential composition in the Java sense, just one line after another. And also it can be loops. We'll talk about loops as well eventually. So I think the lecture here really got practical value, even though we don't really do programming per se. But I think to really study about program behavior statically on the paper is very valuable before you graduate from this course. Okay, so now we're going to see how we can calculate WP systematically, right? So now, for those of you who really want to take some programming challenge, think about how you would define your S over here, the programming statement over here is more like a composite structure, right? Define S as a composite structure, and then see how you can define a visitor, which will be to calculate the weakest precondition. Okay, this is only for those of you who want some challenge. Okay, that in the lecture we don't really talk about how you can implement it, but it's doable. Okay, so now I want to talk about very quickly how we can do weakest precondition. Okay, to calculate. Before that, let me just go over quickly. So now here we already talked about it, right? So we say in this case, we just assume n larger than 4 is the weakest precondition. You can go over this slide. Everything has been set already in the iPad illustration. Okay, I'm not going to waste your time. So now, also before we talk about the first rule for WP, so now let's talk about some syntactic convention. So now, usually in the postcondition for your x, remember in IFO we got x versus old x. You can think about x is like a post-state value. Old x is like a pre-state value. But now in the math, you may just want to say x with a subscript 0 to denote the old value. Okay, you will see examples as we go through. And also x without a 0 subscript will be the post-state value. And then we got precondition. So now in the precondition, everything is in the pre-states. So in that case, we don't have to say 0 always. But anyway, so in this particular case, you can say B0 larger than A. Apparently B0 is a pre-state value, but you don't have to, because in the context of this bracket here, everything is in the pre-state. On the other hand, for the post-condition over here, you can see here we say the post-state value B equal to the pre-state value B minus A. It's more like a withdrawal kind of concept. Okay, so these are some syntactic convention here. You can also go over them before Wednesday. Okay, so I only want to cover one single rule for today. Hopefully we can finish that, and then I will see if I got time to do some simple example. We'll see. Let's say this. So our first example here, we want to calculate the WP. And then WP here, given some very simple program, which is only to assign value E, some expression E, into variable X. So that means in the post states, X is going to become the value of E. And then we're saying that after this particular assignments, the post condition R must be established, right? That's exactly the WP. So now we're asking what should be the weakest precondition for this to happen, okay? It turns out this is the rule. Of course, I can already stop you from memorizing this, but I would say let's try to get some intuition so that'll be easier for you, okay? Let's say this here, I prepare something for you. Let's say, for example, let's say a very simple program. Let's say if I have X, let's say for the implementation, X is assigned to X plus 1. Okay, how about this? Let me say minus. The implementation would be we want to modify X such that X becomes its pre-state value minus 1. Okay, this is assignment, of course. And then let's say the post condition we have is X should be larger than 0. Okay, so now that's something we want to see. And then the expression over here is more like an X minus 1, right? That's just one example. You can see X is assigned to X minus 1. And then we want to make sure after we have done this, it's now going to be X larger than 0. You can think about the X over here is a post-state value. Okay, the post-state value for X. So now what should be the WP? And notice that when you talk about the WP, it's actually a precondition, which means all the values, especially X values, should be in the pre-states. So now what should be the weakest precondition for that? Okay, according to the rule, it is saying that in order to calculate this particular WP, you want to say take the same R over here and then replace every free occurrence of X by E. Okay, that's what it is saying. For example, let's say this. If I got X equals 3 over here, we know that it's now going to be substituted into X minus 1. In that case, it would be X equals, so now 3 will be 3 minus 1, right? So now it will be 2, basically, right? I'm just trying to go a little bit deeper so you will see the insight into this particular one, but it's a very simple rule, okay? And similarly, so now, in general, if I got some value X, after this particular substitution, X is going to become E. So now when I say X should be larger than 0, it's as if I said E should be larger than 0, because E has been used to replace every occurrence of X. So whenever you mention about X over here, whenever you talk about X over here, you're really talking about E, which we just used for substituting X. Okay, guys, any questions for this? So what we just talked about is the very first WP rule. So I think I'll just take maybe another 1 or 2 minutes to do one simple example, and then we're done. Okay, just bear with me. So now, again, this particular rule, if you got X is assigned to E, in that case, in every occurrence of X in R, you're going to substitute it by E. Okay, that's basically what we're going to do. Let's do one example over here very quickly. So now this is also on your slides, but I think I'll do it together with you very quickly. So now, what is the weakest precondition for this particular program? Let's say this is the implementation and this is the postcondition, right? So now how do we calculate that, right? So now let's calculate it quick together, okay? So now the calculation of WP is very fundamental when you want to prove the correctness of your program, right? So let's try that together. So now if I want to calculate WP over here, WP, it's going to take 2 arguments over here. The first argument is going to be the implementation. X is assigned to X plus 1, okay? And then the second argument is going to be the postcondition. In that case, it would be the postcondition here. So X larger than X0. Okay, that's how you write it out. So make sure, since we want to do systematic calculations throughout, so you want to make sure the syntax is actually as correct as possible. Okay. So now, in order to calculate this, okay, we'll do the equational style of arguments. So WP should be equal to, you will see the equal sign here, and then you will just give a reason. So here you can say WP rule for assignments. Okay, so now the rule for assignment is it's going to be the same postcondition R, which will be X larger than X0, right? You can think about X larger than X0 is like the R over here. And then we're going to replace every occurrence of X by E. And then what we want to do is we want to replace every occurrence of X by this particular E. You can think about this is E, right? So let's be a little bit more precise over here. So when you talk about X plus 1, so think about this X over here is really about the pre-state value. The pre-state value, right? So more precisely, so what it really means is X0 plus 1. So it's going to be the postcondition, except that every mention of X is now going to be replaced by x0 plus 1 because that was exactly the assignment that we were trying to do in the implementation. Okay, let's do the substitution very quickly. So now once we do that, let's do this. So now every occurrence of x, okay, let me just use a different color. Every occurrence of x, so now this is the only x, right? Not this x0, just x. Replace it by x0 plus 1. So what you will get, let's do some simplification. So now this will be equal to x0 plus 1 larger than x0. Okay, so also good? Okay, so now if you try to simplify that a little bit, you can cancel these two things out. What you will get is 1 larger than 0, and that is equal to true. So true, it turns out to be the WP. Okay, so now WP is actually true. So now what does that really mean? Does it really matter what question mark here, does it really matter in this particular case? Does it matter? So now would you agree? Any precondition Q I put over here, Q simply implies true. Regardless what Q is, because anything is a subset of true, exactly right. Okay, so now since this is the case that, so now that means in this particular case, does it really matter? No, it doesn't really matter. Let me write it down and then we are done. Okay, so now for this program, because the WP is true, any precondition is stronger than that. So for example, if you put simply precondition true over here, that's okay. If you put a precondition, let's say x is larger than 0, that's also fine. So any precondition for this particular program is fine because you can always discharge, you can always prove this as a theorem. Okay, guys, any questions, please? Any quick question? I know I'm running over time, but I do appreciate your patience. But any question, quickly? Okay, very good. So I would say on Wednesday, we're going to start talking about some other WP rules. But I would say before Wednesday, please try to review what we said today about everything about the background. Also WP, about Hoare triple, etc. That's something I will assume you know about on Wednesday's lecture. Hopefully Wednesday we can cover more WP rules. And also we can talk about loops. Okay, if no question there, I will stop here and then I'll see you on Wednesday. Thank you.